90 seconds. That's it. That's the whole game. The moment your body hits the vacuum of space, no air, no pressure, nothing holding you together the way you're used to, you've got about 90 seconds before it's over. Not minutes, not if you're lucky. 90 seconds every single time, no exceptions, no countdown, no warning siren. Definitely no big dramatic explosion like the movies love to show you. Just silence, and a clock that started the second the air left you, whether you're ready for it or not. But here's the part nobody puts in the title. You won't even be conscious for most of that time. And the way your body actually fails, it's got almost nothing in common with what movies have trained you to expect. So let's walk through this, second by second. But first, why does this even matter right now? And not just as some morbid thought experiment. Because for most of spaceflight history, that's exactly what it was. A hypothetical. Something buried in physiology, textbooks, and worst-case training manuals. Not anymore. Private companies are selling seats on spacecraft now. To regular people, not just trained government astronauts. That would have sounded like straight-up science fiction 20 years ago. Back when space belonged exclusively to a handful of governments with the budget and the political will to get there. In 2024, a mission called Polaris Dawn pulled off the first fully commercial spacewalk. Civilians, not career astronauts, briefly exposed to the same conditions we're about to break down. Hundreds of kilometers above Earth, in suits built and tested by a private company instead of a government agency. And Starship? It's designed to carry more people into vacuum-adjacent environments than anything humanity has ever built. Dozens of passengers, routine flights, no astronaut training required. This isn't a someday, maybe scenario anymore. The odds are climbing with every single launch on the schedule. Okay, let's kill the Hollywood myth first, because believing it could get someone killed in a real emergency. In the movies, a body hits vacuum and boom, explodes outward, or freezes solid, mid-scream, like the vacuum's some kind of monster waiting to pounce on anyone unlucky enough to fall into it. Neither one is true. Your skin and connective tissue are strong enough to hold the pressure difference together. You're not popping like a balloon, no matter how good that shot looks in a trailer. And you're not flash freezing either. Space barely has any matter in it to pull heat away from your body. So heat loss out there is way slower than people assume. What really happens is stranger, and a lot more specific. It's called ebulism. Here's the idea. Without atmospheric pressure keeping your body's fluids liquid, they start to vaporize, to boil, at completely normal body temperature. Not from heat, from the total absence of pressure. The saliva on your tongue would start boiling away within seconds. It sounds like science fiction. It isn't. Every stage of this has been measured, documented, reproduced under controlled conditions in labs specifically built for this kind of research, which is why flight surgeons can describe it this precisely instead of just guessing. And here's the part that should mess with you a little. You don't even need true vacuum for this to start. Around 19 kilometers up, a line called the Armstrong Limit, named after Harry Armstrong, the Army physician who first documented it back in the 1930s. Pressure already drops low enough that water boils at body temperature, and you're still technically inside Earth's atmosphere. High-altitude pilots train for suit failure right at that line, long before anyone even gets close to orbit. Cold War U-2 and SR-71 pilots basically lived above it, wrapped in full pressure suits, for that very reason, because up there the physics is functionally identical to open space. Now, the 15 seconds. This is where it gets real. Your lungs, already emptying because of the pressure difference, stop pulling in anything useful almost instantly. And if your instinct is to hold your breath, that's the worst thing you can possibly do. The pressure gap can rupture lung tissue in an instant, and force air straight into your bloodstream. A fatal air embolism before oxygen deprivation even becomes the real problem. Every decompression protocol on Earth, from military ejection training to spacecraft emergency checklists, teaches the exact opposite of what feels natural. Exhale. Fully. Keep exhaling. 10, maybe 15 seconds in, oxygen-starved blood hits your brain, and consciousness doesn't fade the way it does when you're falling asleep. It drops off a cliff. Vision tunnels. Thinking clouds almost instantly. Then it's just gone. This is the window where rescue can still work. And it's the only reason mission controllers train so obsessively for those exact 15 seconds, running the same emergency drill over and over until the response becomes pure muscle memory. Your blood, by the way, won't boil the dramatic way people picture it. Your circulatory system holds enough internal pressure to buy some time there. Blood vessels act almost like a built-in pressure suit, flexing and holding rather than rupturing outright. But every exposed surface, your eyes, your mouth, any bare skin, starts boiling almost immediately, and your body starts to visibly swell because trapped gas inside you is expanding with nothing left to hold it back. Every animal study on brief vacuum exposure has documented this same thing over and over in the same order. None of this is theoretical, by the way. In 1965, a NASA technician named Jim LeBlanc was in a vacuum chamber at the Johnson Space Center testing a prototype spacesuit, a routine test, the kind that had run smoothly hundreds of times before. Nothing anyone in that room expected to go wrong. When his pressure hose disconnected. The chamber was already pumped down to near vacuum. For about 14 seconds, LeBlanc was fully exposed. He said later that the last thing he remembered was his saliva boiling and the feeling of touch fading before his vision even did. Technicians caught it almost instantly and scrambled to repressurize. Got it done in about 27 seconds. LeBlanc survived. No lasting damage. And his 14 seconds became one of the most important data points in the entire history of spacesuit safety. So why does a spacesuit even work? One reason, it holds that 90-second clock at bay. A modern EVA suit isn't just an oxygen tank with a helmet. It keeps internal pressure at roughly a third of sea level, just enough to keep your fluids liquid, wrapped in multiple layers built to survive micrometeorite strikes, brutal temperature swings, and the constant risk of a slow leak nobody notices until it's too late. That fabric and those sealed joints, that's the entire margin between a routine spacewalk and a catastrophe. Engineers spend decades refining every stitch of it because the cost of getting it wrong isn't measured in warnings. It's measured in seconds. Puncture it badly enough and the clock starts anyway. Suit or no suit. And every engineer who's ever worked on one knows which 90-second clock they're really racing against. Before we go any further, if any of this is messing with how you thought this worked, that's why this channel exists. Hit subscribe now, because the story you're about to hear, it's the one where that clock actually ran out. June 1971. A Soyuz 11 capsule is heading home after nearly 24 days aboard Salyut 1, the world's first space station. Longer than any humans had ever spent in orbit, up to that point in history. During separation of the descent module, a pressure equalization valve malfunctions. Opens early, already in the vacuum of space. Cabin pressure hits zero in about 30 seconds, and nobody on the ground has any idea anything's wrong. Georgy Dobrovolsky, Viktor Patsayev, Vladislav Volkov. None of them were wearing pressurized suits during that phase of the flight. Mission design at the time considered the descent module sealed, safe enough that suits weren't required once the crew strapped in for re-entry. The capsule lands under parachute, right on schedule. Looks completely normal from the outside. All three were already gone. To this day, they remain the only human beings ever confirmed to have died in the vacuum of space itself. The investigation traced it back to that one valve. The fix, looking back, was almost embarrassingly simple. The kind of thing that makes you wonder how it wasn't caught during testing in the first place. But the consequences reshaped an entire space program. Pressurized suits during ascent and descent became mandatory on every crewed mission that followed. A rule every astronaut since has quietly relied on, without ever having to find out the hard way like that crew did. Here's what almost nobody connects to that tragedy. The vacuum that killed them isn't some rare hazard, locked away in test chambers and worst-case scenarios. It's the default. It's what the universe really is, almost everywhere. More than 99.9% of the observable universe is vacuum. Stars are rare. Planets are rarer. A place where that 90-second clock isn't already running? Rarer still. Earth, and maybe a thin scattering of other worlds we haven't even confirmed yet, is the exception to a rule that governs pretty much everything else that has ever existed. Every spacesuit, every sealed capsule, every pressurized module humanity has ever built exists to do one thing: carry a tiny fragment of the bubble you're sitting inside right now, somewhere it was never meant to go. You're not even thinking about that bubble as you listen to this. Soyuz 11 didn't fail because space is uniquely cruel. It failed because the gap between that bubble and its absence comes down to one valve, one seal, one decision about when to put on a suit. A margin so thin that an entire mission can go perfectly, right up until the final 30 seconds. So maybe the real question was never whether you could survive 90 seconds in the vacuum of space. Maybe it's this. Right now, on the only surface in the observable universe where that clock isn't already counting down, what exactly are you doing with the time you have?